moves through the screen, okay? There we go. As it's moving, we see that the laser, if we just follow the path of the laser, is not straight up, it's a bit on a diagonal, isn't it? And that has to do with the fact that the train itself is moving. And if we see it further down, we see that it reaches back to the original laser at this point. So yes, it still launches from the laser, hits the mirror, and goes back to the laser. But for someone who's unable to move along with the laser, it looks like this zigzag instead of a straight line up and down. So allow me to put the little arrows there. Okay, but this is bringing up a very interesting result. Is that distance d in the first diagram the same as this entire distance from here to here? Absolutely not. That little d up there is smaller. It appears to someone who's not inside the train that that laser traveled a greater distance. And we can compare these two values. So we can write down what the time was, and instead of t up here, I'm going to change that to delta t. Delta t talks about a time interval, okay? And not only that, I'm going to put a little p here as well to refer to proper time. And I'm going to call it proper time because that is the time measured in the frame of reference of the laser itself, right? So let's see if we can calculate what this new time is. Well, it turns out with some fairly basic mathematics, which I'm going to have you go over in your tutorials, we can derive that the time it takes to go from this location to this location is just 2d divided by c, multiplied by this brand new term, 1 divided by 1 minus v squared over c squared, all rooted. Okay, looks a little complicated. It's not. C is a constant. V is the only unknown in that entire equation, isn't it? So all that V depends on is how fast the train was going. So this is going to give us a completely different value than delta TP. Why? Because look, 2dc is delta TP. So this just becomes delta TP multiplied by gamma. So the time it takes to go from that first launch to this one is going to be the actual time it takes multiplied by this new term that we've learned now called gamma. And this gamma term is going to alter the time. So what have we just shown? We have shown time dilation. That time itself is not absolute. Now this is one of the counterintuitive things that I was talking about, right? We hadn't realized that if we measure some time interval in our frame of reference, that is not the same time interval in another frame of reference. And we'll see why we haven't realized that in the past. But this has been verified experimentally. We have measured the exact value of this change in a number of ways. One of the most popular ways was done with atomic clocks, these high precision instruments that will tell you what time it is to a very, very high degree. What they did was they put a bunch of atomic clocks, they synchronized them, and put them on airplanes and kept one on the ground. These supersonic jets then took off, went in all different directions, and then came back and landed. They were then compared to the clock that was on the ground. And with a little bit of mathematics, there was a difference. They realized there is a difference between these times, and it was approximately what you would expect with special relativity. A huge example of special relativity at work. Also in high-energy particle accelerators, nuclear reactors, we use special relativity every day to make those devices work and to make measurements from those devices. And lastly, the Global Positioning Satellite System. Has everyone heard of the GPS? You know what a GPS is, right? It's a system that tells you where you're located on Earth. And it works by having a bunch of satellites in outer space that spin around the Earth very, very quickly. They go around the Earth within, I think, I'm not sure what the exact time is, but they're moving a lot faster than people here on the surface of the Earth. And because of that, time changes different for them than it does for us here. And by knowing exactly what that difference is through a simple time dilation calculation, we can compensate for that, and the GPS is incredibly accurate because of special relativity. If not, it would lose quite a bit of time over an extended period of time, and those GPSs would not be able to be as accurate as they are today. So a whole bunch of real-life examples of time dilation at work. But why don't we see this phenomenon in our everyday lives? How come it's so counterintuitive? Well, let's do an example where we should see it in our everyday life. Okay, let's take this scenario. So you're driving home, okay? And let's say you're driving to your family's house and it's a good 5 hours away. You're taking the 401 and you tell your family you're going to be there in exactly 5 hours. You get in your car and you drive down the highway. Let's say you have a velocity of 108 kilometers an hour. A little over the speed limit, but probably won't get stopped. That's exactly equal to, or approximately equal to 30 meters per second. We leave it in meters per second because it's a lot easier to deal with. When you get to your family's house, they say that you're late. They're claiming, hey, why are you so late? You said you were going to be here in 5 hours. The excuse you give is, hey, you know what? I was traveling so fast that 5 hours passed for me, but it must have been a lot longer for you. That's your excuse. You know what I'm saying? I was driving so fast that I'm late getting here. Is this a realistic excuse? Let's find out. Okay, so what else do we know? We know that the trip, according to the frame of reference of someone on the Earth, took 5 hours. So we'll write delta t is equal to 5 hours. And first thing we need to do is figure out what this gamma term is. So we can figure